lesson, all three of us are going to talk about applications involving systems of linear equations in two variables. I'm going to start with a word problem. Then I'm going to look at a couple of applications involving money, and I'm going to end with a nutrition application. So let's look at that word problem. One number is 62 more than another. If twice the larger number is subtracted from 5 times the smaller number, the result is 155. What are the two numbers? One thing we always want to remember to do when we're solving a word problem or an application is to remember to define your variables. So what are our variables in this case? Well, we're talking about a couple of numbers, a smaller and a larger number. So let's let x represent the smaller number, and y represent the larger number. Now I need to write a system of equations. What information am I given? Well, I'm told one number is 62 more than another. So the larger number must be 62 more than the smaller number. X is the smaller number, so x plus 62 should give us the larger number y. We're also told if twice the larger number is subtracted from 5 times the smaller number, the result is 155. So we're starting with 5 times the smaller number, that's 5x. And we're subtracting from that twice the larger number. That means 2 times the larger number, so 2y. And the result is 155. So 5x minus 2y equals 155. This is the system of equations I need to solve. So let's go ahead and solve the system. The first equation is already solved for y, so the system seems to be set up for substitution. So let's substitute x plus 62 for y in 5x minus 2y equals 155. What does that give us? Well, it gives us 5x minus 2 times the quantity x plus 62 equals 155. Now I can solve this equation for x. Let's distribute the negative 2. So 5x minus 2x minus 124 equals 155. Combining like terms, I have 3x minus 124 equals 155. Adding 124 to both sides, I have 3x equals 279. Dividing both sides of the equation by 3, I have x equals, well, let's see, 3 goes into 27 9 times, and 3 goes into 9 3 times, so x is 93. I still need to find out what the other number is. Well, x was defined to be the smaller number, y the larger number, and when I add 62 to the smaller number, I'm supposed to get the larger number. So if x equals 93, then y should be 93 plus 62, which is 155. So it looks like our two numbers are 93 and 155. Of course, we need to make sure that this really is true. In an application, you want to go back to the statement of the problem and make sure that your solution checks in the wording of the original problem. So we were given two pieces of information. One number is 62 more than another. So if I add 62 to the smaller number, if I add 62 to 93, I should get the larger number. What is 93 plus 62? Well, it's 155, the larger number. So that checks. I'm also told if twice the larger number is subtracted from 5 times the smaller number, the result is 155. So I'm subtracting 2 times the larger number, so 2 times 155, from 5 times the smaller number, 5 times 93. I'm going to pull out a calculator to do this calculation. So I need to take 5 times 93 and subtract 2 times 155. and that gives me 155. This is good. Our problem told us that the result of the subtraction was 155. So this checks, and I can formally state my conclusion now. The two numbers are 93 and 155. Well, now let's look at some applications involving money. Tickets for Pink Floyd's Laser Light Show were $8 for children and $10 for adults. For the Friday night show, 234 tickets were sold for a total of $2,176. How many of each type of ticket were sold? Well, as with any application, I need to start by defining my variables. What are my variables in this problem? Well, I have two different types of tickets that are being sold. So let's let C represent the number of children's tickets that were sold. And A represent the number of adult tickets that were sold. Now I need to come up with a system of equations. Sometimes it's helpful to use a table to write our system of equations. In this table, I have a column for number of tickets and a column for revenue. My rows are having to do with the child's tickets, the adult's tickets, and the totals. Well, I know my totals. I know the total number of tickets is 234. That was given in the problem. I also know the total revenue was $2,176. My variables were the number of child's tickets and the number of adult tickets. So I'll go ahead and put my variables in this first column, C and A. To find out how much money was made from the sale of the child's tickets, I need to take the number of children's tickets that were sold and multiply it by the price. Children's tickets sold for $8 per ticket. So if I multiply 8 by C, I get the revenue from child's tickets. What about the adult's tickets? Those are $10 each, so if I multiply 10 by the number of tickets A, I get the revenue from the adult tickets. Now these two columns in the table actually lead to my equations in my system. In the first column, if we add up the number of children's tickets that were sold and the number of adults' tickets that were sold, we should get 234. C plus A is 234. If we, in the second column, add up the revenue from the children's tickets to the revenue from the adults' tickets, we should get our total revenue of $2,176. So 8C plus 10A equals 2,176. Well, let's take the system of equations and solve it. So I have C plus A equals 234, and I have 8C plus 10A equals 2,176. Now I think I want to solve this system by the elimination method. So I need to eliminate either the variable C or the variable A. I think it's easier to multiply by 10 than to multiply by 8, so I'm going to go ahead and eliminate A. I also need opposite signs on my coefficients, so I'm going to multiply the first equation by -10 on both sides. So that gives me -10C minus 10A equals -2,340. And taking my second equation as is, 8C plus 10A equals 2,176. Now when I add the sides of these equations, on the left, -10C plus 8C is -2C. -10A plus 10A is 0. That's good. We wanted to eliminate the variable A. And on the right-hand side, Negative 2,340 plus 2,176 is going to be negative, well, let's do the subtraction. 4, 6, 164. So if I divide both sides of this equation by negative 2, that gives me C equals, I'm dividing a negative by a negative, so positive 82. I'd be worried if my answer came out negative. Remember, C represents the number of children's tickets. So I still need to solve for the number of adult tickets that were sold. So if C equals 82, then working with our first equation, C plus A equals 234, we have 82 plus A equals the 234 tickets that were sold. Subtracting 82 from both sides of this equation, I have A equals 152. So let's check this. We were told that there were 234 tickets that were sold. What happens if I add the 82 children's tickets to the 152 adult tickets? Well, that total is 234. That's good. That's what we wanted. What about the total revenue? Well, if I take my $8 per ticket for the children's tickets and multiply that by the 82 tickets and add that to the $10 per ticket for adult tickets multiplied by the 152 tickets, what do I get? I think I'm going to pull out my calculator for this one. So I need to take the $8 per ticket times 82 tickets plus $10 per ticket times 152 tickets. And that gives me 2,176. This is good. We were told the revenue was $2,176. So both of the pieces of information we were given check with the answers that we came up with. So we can say there were 82 children's tickets and 152 adult tickets sold Friday night. Well, let's look at another application. We're choosing between two plans at a discount warehouse. Plan A offers an annual membership fee of $300 and a 30% discount on merchandise. Plan B offers an annual membership fee of $40 and a 10% discount. How much merchandise would you have to purchase in a year to pay the same amount under both plans? What would the cost for each plan be? Well, the first thing we need to do is define our variables. What are our variables in this situation? We'll look at the two questions. How much merchandise would you have to purchase in a year? And what would the cost for each plan be? Let's let M represent the amount of non-discounted merchandise in dollars, and C represent the total cost in dollars of the plan. I've had the computer pre-print the definition of the variables. You're going to see this off and on throughout this lesson just as a way of saving time so that we can show you the maximum number of examples. When you're writing a solution, you need to make sure that you write down your definition of the variables. So using these variables, we need to come up with a system of equations. So going back to our problem statement, Plan A offers an annual membership fee of $300 and a 30% discount on merchandise. So if we're looking for the total cost, we called that C, of Plan A, well, we start with the $300 membership fee, and then we get a 30% discount on merchandise. A 30% discount means we're going to be paying 70% of the non-discounted price. 70% in decimal form is 0.7. So I'm going to take 0.7 and multiply it by M. That was the variable for the amount of non-discounted merchandise. Now I want to do the same thing for Plan B. In Plan B, the total cost is going to be that $40 membership fee, plus, well, here we have a 10% discount on merchandise. That means we're going to be paying 90% of the non-discounted price. 90% in decimal form is 0.9, so I need to multiply 0.9 by m. Now we have a system of equations to solve. Notice that in this system, both equations are solved for c, so I can use substitution here. So let's substitute the 300 plus 0.7m from the first equation for c in the second equation. And that gives us 300 plus 0.7m equals 40 plus 0.9m. Now, but before I go ahead and solve this equation for m, I want to point something out here. What we've just done is use the transitive property of equality. The transitive property of equality just says if c equals a and c equals b, then a is equal to b. So we used substitution, but in this case, our substitution was just an application of the transitive property of equality. So let's go ahead and solve our equation. I'm going to start by subtracting 40 from both sides of the equation. So I have 260 plus 0.7m equals 0.9m. Now I'm going to subtract 0.7m from both sides of the equation. That leaves me with 260 equals 0.2m. Now let's divide both sides of the equation by 0.2, which will leave me with m isolated on the right. Dividing 260 by 0.2 is the same as dividing 2600 by 2. That's 1300. Remember, m was the amount of non-discounted merchandise. We still need to find c. What would the total cost of the plan be? So let's work with the first equation. If m equals 1300, then c equals 300 plus 0.7 times 1300. Let's pull out a calculator to figure this one out. So I need to take 300 plus 0.7 times 1300. That gives me 1210. So it looks like my proposed solution is that $1,300 of non-discounted merchandise will make the total cost of both plans $1,210. I need to check this though. So let's go back to the original statement of the problem. We actually already checked Plan A. We knew that with the $300 fee and paying 70% of the non-discounted price, that was the $1,300, the total cost ends up being $1,210. Well, let's do the same check for Plan B. We're starting out with a $40 membership fee, and then we're paying 90% of the non-discounted price. So to this, we need to add 0.9 times 1,300. Pulling out the calculator again, 40 plus 0.9 times 1,300 is equal to 1210. This is good. This is what we wanted. The total cost for each plan is the same when we purchase $1,300 worth of non-discounted merchandise. So we can go ahead and write the conclusion. The total cost of each plan is $1,210 if you purchase $1,300 worth of non-discounted merchandise. Well, which plan is better if you buy more than $1,300 worth of non-discounted merchandise in a year? Well, it makes sense that the plan that's giving the bigger discount, that was Plan A. Plan A gave the 30% discount, would be the better deal. As soon as we get past our break-even point, we found that to be when the total amount of non-discounted merchandise was $1,300. Just to verify this, let's look at a graph. Notice that on the graph, Plan A starts out on top. That makes sense. Plan A started with a $300 membership fee, whereas Plan B only started with a $40 membership fee. And Plan A stays on top until our point of intersection, our break-even point at $1,300, $1,210. Once we get past the break-even point, Plan B comes out on top, which means Plan B is more expensive. Plan A is going to be the better deal when you've spent more than $1,300 on non-discounted merchandise. So let's go ahead and write our conclusion. Plan A is better if you purchase more than $1,300 worth of non-discounted merchandise in 1 year. So now let's look at a nutrition example. Whitney is planning a low-carb dinner of roast beef and green beans. She wants the meal to consist of 380 calories and 27 grams of fat. If a 3-ounce serving of roast beef has 220 calories and 18 grams of fat, and a half-cup serving of green beans has 20 calories and 0 grams of fat, how much of each should she prepare? Well, let's let R represent the number of 3-ounce servings of roast beef, and G represent the number of half-cup servings of green beans. Using these variable definitions, let's come up with our system of equations. Well, let's start out with the calories. We know that a 3-ounce serving of roast beef has 220 calories. So if we take our 220 calories and multiply it by our number of servings of roast beef, which we called R, we'll get the total calories from roast beef. And then if we take the 20 calories for the half-cup serving of green beans and multiply that by the number of servings of green beans, which we call G, this total Whitney wants to be 380 calories. Now let's look at the fat. She wants her meal to only have 27 grams of fat. A 3-ounce serving of roast beef has 18 grams of fat. So if we take the 18 grams of fat and multiply it by the number of servings of roast beef, that will tell us how much fat is in the roast beef. Green beans don't have any fat, so here we're adding 0 grams of fat from the green beans. She wants this total to be only 27. So our system of equations is really 220R plus 20G equals 380, and 18R equals 27. Let's solve this system. Well, that second equation is easy to solve for R. So I have 18R equals 27. If I divide both sides of the equation by 18, I have R equals 27 over 18. 27 and 18 are both divisible by 9. 27 divided by 9 is 3, and 18 divided by 9 is 2. So R is 3/2. I still need to find out what G is. I can use my first equation to solve for G. So if R equals 3/2, then using our first equation, we have 220 times 3/2 plus 20G equals 380. I can use this equation to solve for G. 220 times 3/2. Well, I'll start by dividing 2 into 220. That's 110. 110 times 3 is 330. So I have 330 plus 20G equals 380. Subtracting 330 from both sides of the equation, I have 20G equals 50. Dividing both sides of the equation by 20, I have G equals 50 over 20, which is 5/2. So it looks like 1.5 servings of roast beef and 2.5 servings of green beans will give the desired calorie count and fat content. Let's check this. So she wants the meal to consist of 380 calories. So if R equals 3/2 and G equals 5/2, then if we take the 220 calories per 3-ounce serving of roast beef and multiply it by the 3/2, 1.5 3-ounce servings, and add to that 20 calories and a half cup of green beans, so 20 calories times the 2.5 servings, which is 5/2 of green beans. We want this to equal 380, does it? Well, let's see. 2 goes into 220 110 times. 110 times 3 is 330. Looking at our second term, 2 goes into 20 10 times. 10 times 5 is 50. 330 plus 50 is 380. That's how many calories she wanted this meal to consist of. Let's check the fat content. Remember, green beans don't have any fat content, so all we have to do is take our number of servings of roast beef, which was 3/2, 1.5, and multiply it by the 18 grams of fat per serving to find out how many grams of fat will be in this meal. 2 goes into 18 9 times. 3 times 9 is 27. Whitney wanted her meal to consist of only 27 grams of fat, and it will. So now we should be able to write a conclusion. Well, our question was actually how much roast beef and how much green beans she should prepare. In our statement of our problem telling about the numbers of calories and the number of grams of fat, we were told about 3-ounce servings of roast beef, and we were told about 1/2 cup servings of green beans. So let's think about this. If we're taking 3/2, which is 1.5 servings of roast beef, and we're talking about a 3-ounce serving, 1.5 times 3 would be a 4.5-ounce serving of roast beef. So she should prepare 4.5 ounces of roast beef, and we found G was equal to 5/2. That's 2.5 half-cup servings. Well, 2 half-cup servings of green beans would be a cup, and then a half more is a 1/4 of a cup, so we have 1.25 cups of green beans. If she prepares this, she'll have a 380-calorie meal with only 27 grams of fat. So now I'm going to turn this over to Anne, who's going to look at some more applications of systems.
In this part of the lesson, as promised, I'm going to do more applications. I'm going to talk about some mixture problems and some problems involving distance, speed, and time. So let's begin. Here's the first problem. How many quarts of pure pigment need to be mixed with paint that is 40% pigment to end up with 24 quarts of paint that is 65% pigment? This certainly sounds like the mixture problem to me. I'm going to set up a table to try to understand what's going on here. So in this problem, I'm looking at pure pigment, paint that's 40% pigment, and I want to end up with paint that is 65% pigment. Let's look at what I'm given. I'm given that I want to end up with 24 quarts of the 65% pigment paint. I can also easily calculate the amount of pigment by taking 65% of 24 quarts. What are they asking for? They want to know how much pure pigment needs to be mixed with paint that's 40% pigment to end up with this 24 quarts. I have two unknowns in this problem. But once I define the unknowns, I can easily figure out how much pigment is in each of these quantities. X quarts of pure pigment have X quarts of pigment. Y quarts of paint that is 40% pigment has 0.4 times Y quarts of pigment in it. Now once I have a table, I can write a system of equations just by kind of looking what's in my table. In the first column, this is telling me that if I add the pure pigment to the 40% pigment paint, I'll end up with 24 quarts. That's what I want to do. The second column is giving me an equation about the pure pigment. I'm adding up the pure pigment and the pure pigment in the 40% pigment paint to get the total amount of pure pigment in the 24 quarts. I've got a system of equations. So let's go ahead and solve the system. Now I'm going to do this from start to finish. I'm going to start by defining the variables. I just used the table to help me understand the problem. So let's go. I'm going to let x represent the amount, and we're measuring amounts in quarts of pure pigment in the mix, and y represent the amount of 40% pigment paint. And I'm measuring y in quarts as well. So I have my system of equations. X plus y equals 24, and x plus 0.4y equals, and at this point I'm going to figure out what 65% of 24 is. So 65% of 24 quarts is 15.6 quarts. So here's my system. I'm going to solve this system by substitution. So working with the first equation, I can easily solve that for y in terms of x. So I know that y is 24 minus x. I can substitute this into the second equation to determine x. So x plus 0.4 times 24 minus x equals 15.6. Let me solve this for x. So x plus, let me just figure out 40% of 24. That's 9.6 minus 0.4x equals 15.6. Combining like terms, I have 0.6x plus 9.6 equals 15.6. And subtracting 9.6 from both sides, I have 0.6x equals 6. So x equals 10. Now I have to determine y. Well, I know from the first equation that the sum of x and y is 24, so y must be 14. I need to check my work. So the way I'm going to check it is in the context of the problem. So I'm going to assume that I am mixing 10 quarts of pure pigment and 14 quarts of 40% pigment paint. If these are mixed, what am I going to end up with? So what I'm going to look at is the ratio of the amount of pigment in the mix over the amount of the mix, the total mix. So let's calculate the amount of pigment in the mix. We know we have 24 quarts in the total mix. So I have 10 quarts of pure pigment plus 40% times 14 quarts, that's 15.6. So I have 15.6 quarts of pure pigment. Looking at the ratio, this should be 65%. So if I divide 15.6 by 24, indeed, I get 65%. So in the context of the problem, my solution makes sense. So I can state a conclusion. 10 quarts of pure pigment needs to be mixed with 14 quarts of paint, that's 40% pigment, to yield 24 quarts of paint, that's 65% pigment. Let's look at another example. The neighborhood coffee roaster sells organic Turkish roast for $10.75 per pound and a lighter Italian roast for $8.25 per pound. A customer wants 10 pounds of a blend of these two roasts and is willing to pay $9 per pound for the blend. How much of each roast should go into the blend? Well, this is a mixture problem as well. And I'm going to start by just defining a couple of variables. My two unknowns here is the amount of each type of roast going into the blend. So I'm going to let X and Y represent the amount, and I'm measuring the quantity in pounds here, of Turkish roast and Italian roast, respectively, in the blend. So as in my last mixture problem, I'm going to create a table to help me understand this problem. I know that I want to end up with 10 pounds of the blend, and the customer is willing to pay $9 a pound. So the customer is going to have a total cost of $90. What I don't know is the amount of Turkish and Italian roast. But with these variables, as I've defined them, I can figure out the cost of the Turkish roast. That's going to be the cost per pound times the number of pounds of Turkish roast. Similarly, I can find out the cost of the Italian roast. Looking at this table reveals two equations. An equation about the quantity of coffee, x plus y equals 10. And a second equation about the cost of coffee. When I add up the cost of the Turkish roast to the cost of the Italian roast, that should equal the total cost of the blend. So now I have a system of equations, and I'm ready to go. So here, again, I think I'm going to use substitution. So the first thing I'm going to do is I'm going to solve for x in terms of y. So working with the first equation, I get x equals 10 minus y. So substituting 10 minus y for x in the second equation, I get 10.75x, which is 10 minus y, plus 8.25y equals 90. So solving this for y, I have 107.5 minus 10.75y plus 8.25y equals 90. Combining like terms, 107.5 minus 2.5y equals 90. Subtracting 107.5 from both sides, I get negative 2.5y equals negative 17.5. And dividing both sides by 2.5, I know the answer is going to be positive, and this is the same as asking how many times does 25 go into 175, and that is 7. So it looks like I'm going to need 7 pounds of Italian roast. Well, here it's very easy to figure out what x should be. X must be 3 pounds. So I have 3 pounds of Turkish roast and 7 pounds of Italian roast. So I want to check this in the context of the problem. So I need to check that the total cost is indeed $90. So the way I'm going to do this is I'm going to take the $10.75 per pound and multiply that by the 3 pounds of Turkish roast in my mix, and add to that the cost of the Italian roast, which is $8.25 per pound, and multiply that by the 7 pounds of Italian roast in the mix. When I do this computation, I'm expecting to get $90, which is how much the customer was willing to pay for the blend. So $10.75 per pound times 3 pounds plus $8.25 per pound times 7 pounds is 90. So my answer checks. So let's state a conclusion. The coffee roaster should mix 3 pounds of Turkish roast with 7 pounds of Italian roast to get 10 pounds of a blend that costs $9 a pound. Here's another problem. Randy went on a 48-mile bike trip. He traveled 20 miles per hour on the fast leg and 12 miles per hour on the slow leg. The whole trip took 3.5 hours. How long was each leg? Well, this doesn't sound like a mixture problem. This sounds like a problem relating distance, speed, and time. And we know that if we multiply an average speed by the amount of time traveling at that speed, we get the total distance traveled. That's what we're going to use to solve this problem. Again, I think I'm going to start by trying to understand what's happening here in a table. So in this table, I have two legs, the fast leg and the slow leg. I know that Randy was traveling 20 miles per hour on the fast leg. I'll just fill that in. On the slow leg, he was traveling 12 miles per hour. What I'm asked for was the length of time of each leg. Well, let's say he spent t hours cycling at 20 miles per hour and u hours cycling at only 12 miles per hour. Can I calculate the distance? Well, I can. Distance equals speed times time. So I know he traveled 20 t miles on the fast leg and 12 u miles on the slow leg. But there's a bunch of information I haven't used yet. I haven't used the fact that he went on a 48-mile bike trip, nor have I used the fact that the whole trip took 3.5 hours. But I can use that now. For example, if I add up the two times, that should be 3.5 hours. And if I add up the two distances, the distance of each leg, that should be 48 miles. Looks like I have a system of equations and I'm ready to solve it. So let's let t and u represent the duration, and we're measuring time in hours, of the fast leg and the slow leg, respectively. I have my system of equations. The sum of the times has to be 3.5 hours. The sum of the distances has to be 48 miles. Let's solve this. I'm going to solve this system by elimination. So I think I'm going to eliminate u. So I'm going to multiply both sides of the first equation by -12. So I have -12t minus 12u equals let's see, 12 times 3 is 36, plus 6 is 42, that's -42. I'm going to add to that 20t plus 12u equals 48. So I'm left with 8t equals 6, so t is going to be 6/8 or 3/4. So t is 3/4. We need to figure out the length of u, the short leg. So now I know that t plus u, so I'm going to write t as 0.75 plus u equals 3.5 hours. So u is going to equal 2 3/4 hours. So I know that the duration of the fast leg was 3/4 of an hour, and the duration of the slow leg was 2 3/4 hours. Now I need to check, and I want to check in the context of the problem. So I want to make sure that Randy did indeed go 48 miles. So if I take 3/4 of an hour and multiply that by 20 miles per hour, that would be the distance of the fast leg, and add to that the 12 miles per hour times the duration of the slow leg, this should equal 48. Let me do the computation. 20 times 0.75 plus 12 times 2.75, that's 48. So everything worked out and we're ready to state a conclusion. So we know that Randy spent 45 minutes cycling on the fast leg and 2 hours and 45 minutes cycling on the slow leg. I chose to discuss time in terms of minutes rather than 3/4 of an hour and 2 3/4 of an hour. One last example. A plane traveled 1,200 miles in 5 hours with a wind on its tail. The return trip with a headwind took 6 hours. Find the speed of the plane in still air and the speed of the wind, assuming that the speeds remain constant. Now this is a big assumption, that the speed of the wind would remain constant for 11 hours. But this is what it's going to allow us to do, a word problem. I'm going to make a table just like in my other examples. Now this problem is going to be a little bit different than the other 3 problems we've worked. Now what do I know? Well, I know that with the wind, the trip was a little bit faster. It took 5 hours. But going against the wind, the trip took 6 hours. What about the speeds? Well, those are the unknowns. And here it's a little bit tricky to think about it. So I'm going to start by just defining my variables. I'm going to let P represent the speed of the plane in still air and W represent the speed of the wind. I'm measuring both in miles per hour. So let's think about how fast the plane was traveling with the wind. Well, we take its speed in still air, and I'm going to add the speed of the wind. I tend to think of this as the wind kind of pushing the plane a little bit. When the plane is traveling against the wind is working against it. So we're going to subtract the speed of the wind from the speed of the plane in still air to get the speed. Now I can calculate distance because I know that distance equals speed times time. So 5 hours times P plus W miles per hour is the distance the plane traveled with the wind. Against the wind, it traveled 6 times P minus W miles. Now there's one bit of information that I haven't used yet, and that's the information that the plane traveled 1,200 miles. First going with the wind and then coming back against the wind. But in my table, if I look at this distance, it has to equal 1,200 miles. And if I look at this distance, it also has to equal 1,200 miles. So I've got a system of equations which I can solve. So when I rewrite my system, I'm going to use the distributive property. 5P plus 5W equals 1,200. 6P minus 6W equals 1,200. I'm going to solve this system using elimination. I think I'm going to eliminate W because the signs of the coefficients are opposite. And I'm going to multiply the first equation by 6 and the second equation by 5. And this gives me a new system, 30P plus 30W equals 7,200, and 30P minus 30W equals 6,000. Adding the two equations, we eliminate W, and we end up with 60P equals 13,200. So P equals the quotient of 13,260. That's the same as 6 going into 1,320. So 6 goes into 13 twice with 1 left over. 6 goes into 12 twice, and I've got another 0. So P is 220. I still need to calculate the speed of the wind, and I can use either of these equations to determine that. So if P equals 220, then using the equation 5P plus 5W equals 1,200, I can solve for W. So I have 1,100 plus 5W equals 1,200, 5W equals 100, so W equals 20. So it seems like the speed of the plane is 220 miles per hour, and the speed of the wind is 20 miles per hour. That's the speed of the plane in still air. Now I want to check, and the way I'm going to check, I'm going to make sure that both of these trips with the wind and against the wind were indeed 1,200 miles. So here's what I'm going to do. With the wind, that was 5 hours. The plane was traveling 240 miles per hour when I add the speed of the plane and the speed of the wind. That's 1,200. Let's make sure I get 1,200 miles on the way back with a headwind. Well, with a headwind, it took 6 hours, and if I subtract the speed of the wind from the speed of the plane in still air, that's 200 miles per hour. That's 1,200. So my solution makes sense in the context of the problem. So I can say that the plane's speed in still air was 220 miles per hour, and the speed of the wind was 20 miles per hour. So that ends this part of the lesson. Steve's going to look at a couple of different applications of systems.